Hello, everybody, and welcome to episode 3.1, the first in a series of episodes focused on resourcing problems. The first episode will start off simple, but the series will grow increasingly complex, introducing new concepts such as serial production, marginal economics, multi-period planning, and inventory management. If you are new to this channel and mathematical optimization, please check out episodes 1 and 2 to get grounded in the fundamentals of mathematical optimization and solving optimization problems in Python. And please don't forget to hit the subscribe button below. To kick off today's episode, I want to talk first about what production resourcing problems are and why we care about solving them. After that, I want to set some groundwork by solving a very simple mixing problem and review its solution. Now, if you've watched episodes 1 and 2, this problem will be the same that we used for those episodes, but it will be done in a much more condensed manner. In part 3, I want to transform this simple mixing problem into a resourcing problem by integrating some mixing processes and equipment. I will walk through the updates needed in the problem description and the necessary changes to the data. And finally, I will walk through how to solve this problem in Python and Pulp. And I'll conclude the episode with talking a little bit about what you can expect in episode 3.2. So what exactly is a production resourcing problem? To start, production resourcing problems, also called resource allocation problems, are very common in many industries, especially in manufacturing. Resourcing problems deal with how to best utilize a finite or limited means of production for the manufacturing of products. Solving these types of problems means determining how a limited set of resources should be allocated in the manufacturing of various components or products such that an objective is optimized. Examples like maximizing revenue or lowering costs. If you look to the right, you will see a simple depiction of a resource allocation problem. The leftmost icons represent raw materials or inputs to a collection of processes, which in this case are represented by the plant icons. These processes can be distinct processes, meaning they are dedicated to the manufacturing of a specific or certain product, or they can be fungible, meaning that they are interchangeable with other resources. On the right, finally, are your products, which could be durable goods, consumables, or specialty products. Oftentimes in these situations, we are dealing with a resourcing problem because our raw materials or demand for our products outpaces the ability to manufacture those products through our collection of processes. We're now ready to set up our problem, and we're going to do that by solving a very simple mixing problem first. This is problem 14 in chapter 2 from An Introduction to Management Science, a Quantitative Approach by David Anderson. Now, if you've seen episodes 1 and 2, this will be very familiar. I'm going to show how to solve this in a very condensed and quick way. And then we're going to transform this problem, as I mentioned earlier, into a production resourcing problem. We are now ready to solve our example problem in our JupyterLab notebook, and I'm going to start by reading the problem description. RMC Incorporated is a small firm that produces a variety of chemical products. In a particular production process, 3 raw materials are blended or mixed together to produce 2 products, a fuel additive and a solvent base. Each ton of fuel additive is a mixture of 0.4 tons of material 1 and 0.6 tons of material 3, and a ton of solvent base is a mixture of 0.5 tons of material 1, 0.2 tons of material 2, and 0.3 tons of material 3. After deducting relevant costs, the profit contribution is $40 for every ton of fuel additive produced and $30 for every ton of solvent base produced. RMC's production is constrained by a limited availability of the 3 raw materials. Down here, I have a depiction of the problem statement. You can see our 3 raw materials, M1, 2, and M3, that are going to be mixed together in different portions to produce either a solvent base or a fuel additive. Recalling our problem-solving process, the first step is to formulate an opportunity statement. I've written it as maximizing profit by determining how much of each product, solvent base, and fuel additive to produce with the raw materials available. Next is our problem definition. Now, for a simple example, this will be just a restatement of the facts from the problem description, but it can get quite extensive for more complicated problems, as we'll see in the future. But we know that our solvent base generates a profit of $30 per ton, and fuel additive generates a profit of $40 per ton. We know that 1 ton of solvent base requires 0.5 tons of material 2, 0.2 tons of material, 0.5 tons of material 1, 0.2 tons of material 2, and 0.3 tons of material 3. We know the 1 ton of fuel additive requires 0.4 tons of material 1 and 0.6 tons of material 3. We know that we're maximizing profits for a single period and we aren't considering any multi-period sales. We know that our raw material availability is going to be limited to 20 tons of material 1, 5 tons of material 2, and 21 tons of material 3, and that we have no ability to purchase additional material. With that, we're now ready to move on to formulating our mathematical model. So in the model development step, we're going to start over here by stating some of our parameters and variables. We're going to let F represent our fuel additive product and S represent our solvent-based product. We're going to let M1, M2, and M3 represent materials 1, 2, and 3, respectively. We're going to declare a new set I, which is going to represent a collection of our products that we make, which in this case is S and F. And we're going to declare a set J, which represents the raw materials used, M1, M2, and M3. We're going to declare a new parameter P sub I, which represents the profit of product I. So for P sub F, this would be $40 a ton, and P sub S would be $30 a ton. We're going to declare a new variable, Y sub I, which is going to represent the amount of product I manufactured. And we're going to declare a new parameter X sub IJ, which is going to equal or going to be defined as the material J consumed per ton of product I. So X sub SM1, which would be the amount of material 1 consumed per ton of product S made, would be 0.5. And that again are these terms up here, the amount of material consumed per ton of product made. And M sub J is going to represent the material J available. So for M sub M1, it would be 20 tons. For M sub M2, it would be 5 tons, and so on. With that, we can start formulating our mathematical model by writing our objective function, decision variables, and constraints. And we'll do this in a condensed way using the mathematical notation that we covered in episode 1. So to start with our objective function, we know that we want to maximize our profit. And our profit is going to be defined as sigma sub I of P sub I times Y sub I. P sub I again represents the profit contribution of product I, and Y sub I represents the amount of product made. So this would be translated to P sub S times Y sub S plus P sub F times Y sub F. So there would be 2 terms to this objective function. We know that our decision variables are going to be Y sub I, which are going to be the tons of product I that we decide to produce. And we are going to have 5 constraints. We're going to have 1 set of material balance constraints and 1 set of lower bound or non-negative production constraints. The material balance constraints represent the amount of material consumed in making our products, S and F, and that must be less than or equal to the amount of material available. So the way that we should read this condensed mathematical equation is sigma sub I of X sub IJ times Y sub I less than or equal to M sub J, and we do that for all J. So X sub SM1 times Y sub S plus X sub FM1 times Y sub F would have to be less than or equal to M sub M1. And then we would construct a material balance constraints also for material 2 and 3. And for our lower bounds, this is essentially saying that Y sub I has to be greater than or equal to 0. And we are going to do that for each of our decision variables, or each of our products, I should say. And so that is our mathematical model. And now we're ready to move on and start solving this in Python and Pulp. So the first step that we're going to take is importing our 3 libraries that we need to solve this problem, which are pandas, which we use for our data management and data frames, NumPy, and Pulp, which of course we use for building the mathematical model in Python. So once we import the libraries, then the next step we're going to do is import the data that we need to solve this problem. Before I go through this specific code, I do want to jump over to our data source. So in the past episodes, I've hard-coded values in for our parameters and variables. But going forward, we're going to be working with data sources, and we're going to start with one of the most common, which is Excel workbooks. So if we pivot over here, this data source has 3 tables. The first table is the products table, which has a list of products in column A and their price or profit contribution in column B. The next table is materials, which has a list of all the materials we'll be using in column A and the quantities available of those materials in column B. And finally, we have our recipe table, which is the amount of material consumed in the production of a given product. So here we've got the products in column A, the materials used to make those products in column B, and the coefficient or the amount of material consumed in making of the product in column A. So jumping back to our Python notebook, to read this data in, we're going to use the pandas library, and we do that with the syntax pd.read_excel. And to this function, we pass two arguments. So the first argument that we pass is the name of the file, and the second argument that we pass is the name of the worksheet. So this tells us where to go get the data and on what worksheet or tab or otherwise table to get the data from. Now, if this data file is not in the same working directory as your Jupyter Notebook, you'll have to precede this file name by the actual directory path as well. And just a quick reminder, we come to the inside of the first open parentheses and hit Shift Tab. We can get a bunch of contextual help for these specific functions. So just a reminder. So we're going to read in the products table and put that into a data frame called data_prd for product. We'll do the same for materials and recipe tables and put those into data frames data_mat for material and data_rec for recipe. And then I always like to view the data frames after they've been imported just to make sure everything looks okay. So you can see here the tables came in and they look just like we viewed them in the data source. So everything looks in order. The next thing that I like to do is I want to put all of my data into data dictionaries, or just shortly dictionaries. And the reason I like to do this is dictionaries are a really handy way to access data or to organize data in a way that allows you to actually select it using subscripts or keys rather to pull out specific data related to certain naming conventions. So a dictionary is kind of like a list, with the exception that instead of subscripting a list by, say, the element like position 1, 2, 3, or 4, you subscript the dictionary by a key, which is usually a name or a string. So for example, we made a dictionary of down here, we make a dictionary of our materials and the quantities. And you subscript this dictionary M by typing in the material name, and then it will return the quantity. So that's how I like to use my data, specifically with pulp. And to start off, to do that, the first thing we want to make are our sets. So I want to make our set of products. So I'm going to make a list of products. And I do that by pulling the column from the data_prd data frame, column product, and I want to get all the unique products in there. Just in case there's duplicates, I always use the .unique. And then I'm going to convert that to a list with this list function. So put this inside these parentheses. I'm going to do the same thing with materials. Data_mat, materials column, get the unique list of materials and convert that to a list. And so now I've got these two lists or sets, one of products and one of materials. Now I'm ready to construct my data dictionaries, which, as you can see here, I have three dictionaries, X, M, and P. And if you recall from our model development, we had a parameter X sub ij, which was subscripted with the product and the material to give us the amount of material consumed in making a certain product. We had a variable M sub j, which was the material available for subscript j, or for the set of materials. And then we had P sub I, which was the profit contribution of product I. So we're going to make dictionaries that essentially do the exact, or essentially reflect our mathematical model. So to make this first dictionary, I'm going to make a key for each product. So X sub I. So I want to make X sub I first. So for P in products, I want to have X and then in closed brackets P, which is going to be the product. So this will be X sub S and X sub F. That's going to make two keys for the dictionary. And then within each of those keys, using this syntax, I'm going to actually make another set of nested keys. To do that, I use this zip function, which basically pairs two lists. And so I give it a list of materials, M1, 2, and 3. And then for the length of that, I basically give it an empty value or none. And so this will make a dictionary for the materials and nest it under each of my product keys. And so what that looks like is shown down here, where I've got this primary key, or not primary, but I've got this first level key of S and F, and then a nested set of keys, M1, M2, and M3. And then as you can see, I've got the values that we had in our table, which are the consumption of these materials in making that product. Now, to populate that table with the values, I have to do another for loop where I actually iterate through each row in our data underscore rec or recipe data frame. And the way that this works is I say for I in data rec.index, so for each of these rows, 0, 1, 2, 3, 4, and 5, I want to assign to this location in the X dictionary this value. And so I say data underscore rec.loc, which is basically short for location in the data frame. And then I give it two inputs. I give it the row number and the column name. So for this first iteration, it'll be I equals 0, so 0 in product, which will give me S. Then I'll have over here data rec.loc I material. So this is, again, looking at row 0 and column material, and I'll get M1. And so now I've spelled out the location in the dictionary, which is X, S, M1. And to that location, I'm assigning this coefficient of 0.5. So data underscore rec.loc, and inside square brackets I, comma, CONS, which is the consumption of that material in making that product. So I loop through each of these rows. It gives you this nice data dictionary down here. I do something similar for M and P. It's a little bit simpler because they're not nested keys, but essentially the same process of creating an empty dictionary and then assigning values to the specific locations in that dictionary. Then I check that I make sure all the dictionaries were built correctly, and it looks as if they are. Now I'm ready to build and solve the model. So the first step, as I've mentioned before, is to actually create the model object. And I do that with the pulp.lp problem method. And I pass two arguments to this .lp problem method. I pass the name of my problem, which I'm calling production resourcing, which technically right now it is not yet, but it will be. I call it production resourcing, and then I tell it the type of problem. Is it minimization or maximization? And I do that with pulp.lp maximize to indicate this is a maximization problem. So I've created my model object. Now I'm ready to create my decision variables. And this is actually a really easy way, this syntax, to create a lot of decision variables at once. So to do that, you use pulp.lp variable.dicts, which is short for dictionary. So this is going to make a dictionary of decision variables for your model. And again, you can hit Shift Tab to get the arguments, but I need to pass four things to this method or function. I need to pass what I want to prefix my variables with. So in this case, I'm going to prefix them all with Y, because as you recall from our model development, we had Y sub I were the names of our decision variables. So I'm going to have Y. And then I'm going to append to that prefix the product. So in this case, this will be the list of products, which is S and F. I'm going to set the lower bound to 0 for all my decision variables, and they're all going to be continuous. And what this spits out is a dictionary of decision variables. So the keys are my products, and the decision variables are, as I mentioned, this prefix and then an underscore with the product name. So dictionary of S and F with the decision variables Y sub S and Y sub F. Now I'm ready to add the objective function. So I create a variable objective function, set it equal to 0, and then I'm going to add the terms to my objective function. So if you recall, again, our mathematical model, we had basically for our objective function, sigma sub I of Y sub I times P sub I. So that was the amount of each product I were making times the profit contribution of I. And we do that for all of I, for all the products we're making. And so to create that objective function, we use pulp.lp sum. And you can read this like a sigma. So this is basically saying I'm going to sum up all the terms, and that's my objective function. So here I'm saying Y sub P. So I'm, again, using the decision variable Y and my key P, which is the product. And then I'm using P, my dictionary I made up here, which is the profit contribution of that product. and again, subscripting it with the key P for product, multiplying those together, and then I'm going to do that for each P in my set products, and that will give me my objective function. So you could read this again as sigma sub I, y sub I times P sub I, and that would be the same as what's shown here. And then I add this objective function to my model object with a plus equals and then objective underscore function. Now I'm ready to do the constraints. So this is a little bit more syntax involved, but again, you'll really start to get the hang of how the mathematical model translates directly to the code. So if you recall, we had a for all materials, right? We're going to make 3 material balance constraints. So that's what this for m in materials is doing, is it's saying, hey, for each material, I need to make a constraint and add it to the model. So that's what this for m in materials is doing. It's creating a constraint with the syntax, and then it is adding it to the model object. And to create each of those material balance constraints, we are actually using what is known as list comprehension. And list comprehension is essentially a way to write a kind of like a for loop, or exactly like a for loop, in a single line. And so what this list comprehension is doing is saying for x sub ij, which again, we're using the keys here, P and M for product and material. So x sub P and M times the amount or the decision variable of how much product we make. So y sub I, or here again, y sub P, where P is the product key. I want to use this to determine how much material I'm consuming for materials 1, 2, and 3, and I want to do that for each product. So this creates a term, x sub ij times y sub I for each product. And then of course the sum is like the sigma, I'm adding them all together. And then that left-hand side, the sum of this, has to be less than or equal to m sub j, or in this case again, m, our data dictionary, with the key of the material to get the availability of that material. So this is that left-hand side, less than or equal to the material availability. I name the constraint here, comma, and then I have a string syntax where I put material balance constraint plus underscore, and then just the name of the material. So M1, 2, and 3. And then I do that for, again, all M in materials. And now I've added the material balance constraints. Step 5 is to write this LP model. So again, for simple stuff, and especially early on, do this every time and get in the habit of writing the LP with .write LP, name it whatever you want, then open it and make sure it built the model the way you want. So you can see here, we've got our production resourcing name up here, that's correct. Maximization is correct. Our objective function is correct, $40 per ton of F times the amount of F made plus $30 per ton of S times the amount of S made, subject to these material balance constraints, which are built correctly here. So we can see we've got the correct available materials, we've got the correct coefficients associated with each of the decision variables. So this looks good. And then we get to the final part here of solving the model. So we've built this model successfully with Pulp. Now we're asking Pulp to go out and enlist the help of a solver, in this case CBC, to get us a solution. So we say model.solve, and then we pass to it the argument, which is the solver, or pointing to the solver that we want to use, which is going to be, in this case, CBC. And then within that solver, I pass 2 messages. Message equals true and keep files equals false. The keep files equals false just prevents filling up your working directory with a bunch of files from the solver solution. And message equals true can be helpful sometimes because actually in the prompt, the Anaconda prompt, when you do run the model, it will spit out a bunch of messages along the way as it's solving the problem. And sometimes that can be helpful in troubleshooting. So we're going to run and solve this, and then we are going to check the status with pulp.lp status, square brackets, model.status, and we get optimal. So everything looks good. I will make one quick caveat. Sometimes if we get to it, which we haven't yet, you can impose a time limit on the solver. It says, hey, I'm only going to give you 3 minutes to find an optimal solution. Now the solver may actually find a solution inside of 3 minutes, but it may not be optimal. In which case, if it finds a solution, but it's not optimal and it hits the time limit, it will still return optimal. So you won't have any way of knowing that. Now, you can tell this by looking at the status code for the solvers, which we'll get to in a future episode, but just something to be aware of. So we've solved it, we got an optimal solution, and now we're ready to evaluate the results and do sensitivity analysis. So model.objective.value will give us the actual objective value, which is 1600. And if you were following along in previous videos, that is the correct answer. And then we want to extract all of the information from the solution. And we do that for our variables and our constraints. And I do that this way, where I make basically an empty data frame to store the results. So pd.dataframe, and then it's empty. I assign that to dataframe underscore bar or df underscore bar. For variables, I want 4 pieces of information. I want what sort of class I'm looking at. So in this case, it'll be variables. I want to know the variable name, the variable value, and whether or not there's a reduced cost associated with the variable. So to start populating these lists, I'm going to say for j and model.variables, which means I'm going to loop through every model variable represented by j. So for j and model variables, I want to append to this list lp underscore class the string var, because I'm looking at variables. I want to append j to var, which is the name of the variable. I want to append j.var value to the value list, which is the variable value, or other words, this is the solution, right? What our decision variable values are. And then to RC, which is reduced cost, I want to append j.dj. So that's how you get these pieces of information from pulp. And then I'm going to create these columns and assign those columns in the data frame the list values. And I get a nice data frame down here with my class, which is variable, my names for the decision variables, y sub f and s, the value of those 25 and 20, and the reduced costs. So you can see for F and S, I made 25 tons of fuel additive, 20 tons of solvent base. I have a 0 reduced cost for both because I made both. Remember, reduced cost only shows up if you don't make anything, because this is reflective of the amount the contribution coefficient would need to change in the objective function for the model to want to make a non-zero positive value for your decision variable. So since we made both, these are 0. I do a similar process for constraints, slightly different. I'm getting a different set of information. So I still want the class, which in this case is constraint. I want the constraint name. I want the left-hand side value. I want the slack, the difference between the right-hand side and left-hand side. And I also want the limit cost, or otherwise known as dual value. So similarly, I do this. I say for jn model.constraints.items, so slightly different syntax. I'm going to append to the LP class list the string constraint. For the list constraint, or const, I'm going to append j subscript 0. So become aware that constraints are subscriptable in pulp because they contain different pieces of information. So to get the name, it's j subscript 0. For the left-hand side, we get back to a summation and a line comprehension syntax, where basically I go over the left-hand side of the constraint. So think x sub ij plus y sub I for all of I. So in this case, we would have 2 terms here, right? So you're looking at these terms on the left-hand side of each constraint. So typically 2 terms, sometimes 1. And what this syntax is doing is saying, I want to take the var.var value, which is again our decision variable value. So how much S we made or F we made, multiplied by the coefficient of consumption for that material. And I want to do that for each variable and coefficient and j subscript 1.items. So in the actual left-hand side equation. So this will all get done and then summed up, and that's the left-hand side value. To get the slack, it's basically j subscript 1.slack and j subscript 1.pi to get the reduced cost or dual value. Again, I take these lists and then I assign them to new columns I'm creating, and I get a nice data frame with my class constraint names for material balance constraint 1, 2, and 3, the values 24 and 21, and the slack 0, 1, and 0, and dual values or limit costs 33, 33, 0, and 44, 44. So what does this mean? We consumed all material 1 and 3. We can see that from the value and the fact that we have no slack, meaning we consumed everything that was available to us. Because these are both constraining the problem, we can see that we have a limit cost associated with those constraints or a dual value. So if we were to increase our availability of material 1 or 3 by 1 ton, we could get an improvement of the objective function by $33.33 or $44.44 for an increase of M1 or M3 by 1 ton, respectively. Material 2 is not constraining. We only consumed 4 of the 5. That leaves us with a slack of 1, and therefore there's no limit cost. So that is the solution to the very simple mixing problem. And now we're going to jump over to a new workbook where we're going to actually talk now about how to transform this into a resourcing or a production resourcing problem with some changes to the problem description and the data set. So I'm going to start here by talking through the revisions to the problem description. So this is more or less the same problem, so I'm only going to highlight the changes that I made. So the first one up here is very superficial. So instead of just, quote, mixing these things together, I actually added a process. So we have to mix and heat these different materials to 300 degrees Fahrenheit in order to make our two products, fuel additive and solvent base. I didn't make any changes to the material consumptions for making the products, but I did make a change down here to the contribution of solvent base to our profit. So instead of making $30 a ton for every, $30 a ton of solvent-based product produced, we're going to make $38 for every ton of solvent-based product produced. So again, this went from 30 to 38, which basically means that the solvent base is now a slightly more competitive product than it was before compared to the fuel additive. And this last part here is really where we transform it into a resource problem or a resourcing problem. So now I'm stating that RMC has 2 mixing units available for production 6 hours a day, Monday through Friday. Both units can mix solvent base or fuel additive. The newer Mixer 1 rate is faster than the older Mixer 2 unit. RMC's production is now constrained by both a limited availability of raw materials and available operating time on each product mixer. The planning department is working to determine the production plan for the coming week, provided the current pricing, current availability of raw materials, and considering that Mixer 2 will be down for 1 day due to maintenance. So we've now taken a simple mixing problem, and now we've added in a process and equipment requirement that we actually have to mix these 3 materials in a mixer and heat that process to 300 degrees Fahrenheit in order to get either solvent base or fuel additive. So we've added this new processing step. And that is how we're going to make this into a resourcing problem. So with that, let's jump to problem definition. So again, only highlighting the changes. Profit contribution here for solvent base is $38 per ton, still 40 for our fuel additive. No changes to the consumption of materials 1, 2, or 3 in the production of solvent base or fuel additive. We're still only looking at a single period. We are not changing the availability of any of our raw materials. We are now adding some new information. So we need to know the Mixer 1 and 2 production rates for solvent base and fuel additive. So for Mixer 1, we can produce 0.65 tons per hour of solvent base. And for Mixer 2, and for fuel additive, we can make 0.5 tons per hour. For Mixer 2, it's a slightly slower rate. So we can only make 0.6 tons an hour of solvent base and 0.45 tons an hour of fuel additive. So what does that mean? That means that if you had 1 hour of time available on Mixer 1 or 2, you could only make these quantities of product. So 0.65 tons is what you could make in 1 hour on Mixer 1 for solvent base. We know that the total production time for Mixer 1 is 30 hours. We get that by multiplying the 6 hours a day of operational time times 5 days a week. And we know for Mixer 2, it's 24 hours because we lose 1 6-hour day due to planned maintenance. We know that we cannot purchase additional material and we cannot acquire or purchase additional operating time. So that means no overtime and no weekend crews to operate the mixers. So again, let's reformulate our opportunity statement. Now we want to maximize profit by determining how much of each product, solvent base and fuel additive, to produce with the raw materials and the product mixer capacities available. It's very similar, but just adding in the new reality that we have a process and equipment tied to these production of these 2 materials. And this is where the this all comes together here, right, in the model development. So how does the mathematical abstraction of this problem change with the introduction of those 2 mixing units? We'll start over here on the left, again, with our parameters and variables. I'll highlight the changes. So the new parameters we're introducing are RX1 and RX2. Okay, this is product mixer 1 and product mixer 2 that we showed up there in the depiction. We're introducing a new set K, which represents the mixers RX1 and RX2. And we're also introducing now a new decision variable, or we're revising our decision variable. So before it was just Y sub I. We're changing this now to Y sub IK. And this is going to represent the amount of product I manufactured in mixer K. It's important to note, I should have said this earlier, that these two mixers are fungible. So you can make either product in any of these mixers. You can make S and F in mixer 1 or S and F in mixer 2. So we actually now have to do more accounting. We need to know how much of each product we're going to make in each mixer, which is why we now have two indices for our decision variables. In addition to that, we also introduced two other parameters, T sub K, which is going to represent the time that's available for product mixer K. So this will be 30 hours for T sub RX1 and 24 hours for T sub RX2, and R sub IK, which is the production rate for product I in mixer K. So again, this would be R sub S RX1, and that would be 0.65 tons per hour. So those are the new parameters. Over here on the mathematical model side, we will update our objective function to reflect the change decision variable. And that's going to require a double sigma or a nested sigma. So for each product on a given mixer, we have to sum P sub I times Y sub IK. And we have to do that for all products in all mixers. So if you were to write this out in long form, it would look like this. P sub S times Y sub S RX1 plus P sub S times Y sub S RX2 plus P sub F times Y sub F RX1 plus P sub F times Y sub F RX2. That's what that double sigma notation would yield. As I noted, our new decision variable is Y sub IK. So again, if you write this out in long form, you would have these four decision variables here, which is the tons of solvent base and fuel additive made on both mixers. And then finally, we get to our constraints. So for our constraints, we can actually see here, that we have the same material balance constraint we had before, but with a double sigma, just like the objective function, we now have to account for the material balance on both mixers. So X sub ij times Y sub ik has to be less than or equal to M sub j. We do that for all materials. And so this would also be, again, if you wrote this out long form, you would have four terms. X sub S M1 times Y sub S RX1, and then you would have X sub F M1 times Y sub F RX1, and then you would have those same two terms, but for the other mixer R sub X RX2, and then all those together would have to be less than or equal to M sub M1. And then you would repeat that again for materials 2 and material 3. We still have the lower bounds. So I just noticed a typo here. The sigma should not be here. So I'm going to pause real quick and clean that up. Okay, thank you. So our lower bound is still here for our decision variables. So it's, again, slightly different. So we have Y sub ik is greater than or equal to 0. So, of course, non-negative production constraint. And we want to do that for all ik. So we're going to have to do this for all four of our decision variables. So 3 constraints here for the material balance, 4 constraints here for the lower bound on each of these 4 variables. And now we would move on to talk about the brand new constraint or set of constraints, which are production time. And this is directly related to the addition of these mixing units. So for the production time, we need to actually determine how much total time is going to be used on each mixer to make our products. And that total time obviously has to be within what has been allotted to each of the mixers. So sigma sub I for Y sub ik over R sub ik has to be less than or equal to T sub k. We will do that for all k. So again, this is Y sub ik. So this is going to be the amount of product I we make on mixer k divided by the rate of production for product I on mixer k. So this is tons, this is tons per hour. The dividing R into Y gives us hours, and we sum that up for each of our products, and then that has to be less than or equal to the total time available on that mixer K, and then we would duplicate this constraint for each of the mixers, so there will be 2 of these. So in total, 4 lower bound constraints, 2 production time constraints, and 3 material balance constraints. Now we're ready to move on and solve this with Python. So I'm going to move a little more quickly through here because we covered some of this already. But step 1, we're going to bring in our pandas, numpy, and pulp libraries. Step 2, we're going to read in our data from our data source in Excel. And I'm going to pop over just briefly to show you the new data elements that we added. So in our new data source, we have the same 3 tables we had before: products, materials, and recipe. What we've added is mixer rates. So this table has the list of mixers in column A, the products that we can make on each of those mixers, and the rate. So you will have duplicate rows for each mixer if it makes more than 1 product, and then the rate. So this says that you can make 0.65 tons per hour of S on mixer 1. The second table we've added is mixer capacity. So column A is the mixer, so RX1 and RX2, and column B is the time available for production. So jumping back over to our Jupyter notebook, we read that data in again using the PD read _ Excel, check our data tables and make sure they came in correctly. They look like they did. And then I'm going to make some new dictionaries. So I'm making the same X sub ij dictionary, the same M sub j dictionary, the same P sub I dictionary, but I'm adding now a new dictionary for R, which is again R sub ik, the rate in tons per hour, right, of what products we can make on each mixer, and T sub k, which is the total time available on each mixer. So following the same descriptions that I gave you already, we make these 2 dictionaries, and R is a nested dictionary, and those 2 lines of code, or those 2 sets of code, give you these dictionaries. So here R sub ik, again, product is the first key, and then a nested key with the mixer, and then the production rates. And then T sub k is just keyed on the mixer, and then it provides the total hours. So we go back through our build and solve process. So we're going to create a model object with pulp.lp problem, name it, state the type of problem, which is a maximization. Then we're going to create our decision variables. And you'll notice something new here. So because I have a decision variable that has more than 1 index, so instead of just y sub I have y sub ik, I'm actually going to make a index with this code, where I make an empty list here, prd _ index, and then I'm going to make a list for P in products and for K in mixers. I'm going to make this prd.index, and I'm going to append to it every possible pair of I and K. So this would be SRX1, SRX2, FRX1, FRX2. And so I'll have this index created. And then I use the same .lp variable .dictionary, or DICTS method, to add a bunch of decision variables to my model. Again, I prefix it with Y. But here, just like I had before that list of products, I now have 2 lists of products and mixers that I'm going to use. And I'm going to create a decision variable using these 2 lists for every product and mixer in my product _ index. So I created this index in order to do this nested list comprehension. And then again, I set the lower bound equal to 0 and category of variable equal to continuous. And I get a nice dictionary here, keyed again on my product and mixer, and I get my decision variable. So the key of SRX1 gives me my decision variable for the amount of S I make on mixer 1. So on and so forth. So I have my 4 decision variables here in a dictionary format. Step 3 is, again, very straightforward, similar before. Create the objective function. I use the pulp.lp sum to actually get each of the terms in my objective function. So this is, again, like that sigma. And what I do inside here is another list comprehension. So y sub I k times p sub I for p and k in product index, or y sub pk times p sub p for p comma k in product index. And that gives me the objective function, which I then add to the model with the plus equals. Similarly, with the constraints, really no change here for the material balance constraints, except again for the new indices introduced for our decision variables. And for mixers, it looks very similar. So I got to make a constraint for each k in mixer. Again, I'm summing up y sub pk divided by r sub pk. So the amount of product I'm making on mixer k divided by the rate of production for that product on k for all of my products. And I sum that up, and that has to be less than or equal to the total time on that mixer. I name it production time underscore string mixer name, and then I repeat it with this for loop for the next mixer. Then I'm going to write my model into LP model here. So I'm actually going to just rerun this whole notebook so we can get the new LP model, and then we can check it. And it looks pretty good. So got a correct name up here, correct problem type. We've got 4 terms with 40, 40, 38, 38 times y sub f rx1, y sub f rx2, y sub s rx1, and y sub s rx2. So that's correct. Our material balance constraints look correct as well. So again, still using the right coefficients. We've got now an additional 2 terms because we're splitting the production across 2 different potential mixers. Material values or material quantities look good. And I see my new production time constraints, which are also constructed correctly. And I see the available times been brought in. So the model was constructed correctly. And then I'm going to solve it as we discussed earlier. And I'm going to look at my model objective value. We can see here it's lower than before. So 1600 prior, now it's 1223.85, which is a good indication that the constraints are probably not material related, but time related, or I should say equipment related. We're going to go through the same process here to extract our variable or decision variable values and information. You can see the data frame down here. I now have my 4 decision variables listed neatly, their values, and the reduced cost. So we can see that we make S solvent base on both mixers 1 and 2, and we make our fuel additive on mixer 1, but we make no fuel additive on mixer 2. And finally, we do have an actual reduced cost here because this is a 0 value. So in order for us to consider or even make F on mixer 2, the profit contribution or the dollars per ton would have to go up by at least $1.03. Again, for constraints, we're doing the same thing here that we discussed before, and we can see our nice and neat constraint table down here with the new production time constraints, and we can tell some pretty insightful things. So first off, from a material balance standpoint, we have sort of a change of fortunes. So material 2 is consumed completely this time. We have no slack, and we have a limit cost to that material of 36.15 or dual value. So an extra ton of M2 would improve our objective value by 36.15. Materials 1 and 3 are not constraining, and therefore they do not have a limit cost in the solution. And we can see both of our mixers are constraining. So we consumed all the time on mixer 1, 30 hours, and all the time on mixer 2, 24 hours. There's no slack, and both of these respectively have a limit cost of 20 and 18.45. So an extra hour on mixer 1 is worth $20, and an extra hour on mixer 2 is worth $18.46. So that is the solution for our now transformed mixing problem into a production resourcing problem. And I will be working next episode to add in a little more complexity. But really what you can gather from this, especially the way that we've constructed the problem with Python using dictionaries and the way we've set up our data sources, is that this isn't a very scalable solution. So adding new components or products, adding new materials, adding new processes or equipment to this would be pretty simple. So again, this is why I really emphasize in practicing how to write this code in such a condensed and general format, because it allows you to build out your model as things get more complex without having to recode too much. So with that, I conclude the episode. And again, 3.2, we'll be adding a little more complexity and looking at serial production.